This is the next video in the series on advanced theories of bonding. We have talked all about molecular orbital theory and orbital overlaps. And now we're going to talk about why that's useful to do. And one of those reasons is to calculate the bond order. So that's where we'll start. So bond order is something we've seen before in a less specific way. When we talked about Lewis theory, VSEPR structure, maybe not so much VSEPR structure, but Lewis theory and valence bond theory. So it's the bond order is simply the number of bonds between two atoms, telling you whether you have a single bond, a double bond, a triple bond, or somewhere in between those options. And we have a simple formula for counting and calculating our bond order, which I've already made an error in. There we go. So the bond order is 1/2 times the number of bonding electrons minus the number of anti-bonding electrons. And that's because the bonding electrons strengthen the bond, the anti-bonding electrons weaken the bond, and each bond is equal to 2 electrons. So we divide that total number by 2 to give us the bond order. So we're going to draw a couple of example molecular orbital diagrams, and we'll calculate the bond order for each one to help us predict the molecular stability of whether those bonds will actually form in real life or not. And in order to calculate the bond order, we need to have electrons in our pictures, which is something that we didn't do before. But I am pleased to tell you that the rules for electron filling are the same as before, exactly the same as when we filled atomic orbitals. And those rules are: we always fill the lowest energy orbital first before the higher energy orbitals. If we have multiple orbitals with the same energy, we occupy them singly before occupying them doubly, so we can reduce that pairing energy. And each orbital has 2 electrons maximum that it can hold with opposite spins. So no surprises here, everything totally within our wheelhouse. Okay, so we're going to draw the 4 simplest MO diagrams that we can, because this is really baby's first molecular orbital diagram discussion, and we're not going to be drawing anything super duper complicated yet. In organic chemistry and in inorganic chemistry, you'll have the chance to draw some more interesting ones. So we're going to look at these 4 molecules: dihydrogen, the dihydrogen cation, a dihelium cation, and a dihelium molecule. And we're going to use the molecular orbital diagrams and the bond orders to predict the stability of each of these molecules and whether we would actually see any of these in real life. So no molecular orbital diagram is complete without an energy axis. We always put the atomic orbitals on the sides, the molecular orbitals in the center. So hydrogen has a 1s orbital, and there's only 1 electron in it. And so those are the only electrons we're going to be able to consider, and the only orbitals that are relevant in this overlap. So we're going to specify what molecule we're talking about by writing the name of the atom below each side, so we remember which atom we're talking about, and below the center, writing the formula for the molecule. So when we overlap the 2 of these, when we overlap 2 orbitals with good overlap, we form a low energy bonding orbital, so sigma 1s, and a higher energy anti-bonding orbital, so sigma star 1s. Remember, the subscript indicates what orbitals it was made out of the overlap from. The letter, Greek letter, sigma or pi, tells you where the overlap is, and the star or lack of star tells you if it's bonding or anti-bonding. So there's a lot of information packed into this one little symbol for the label. And since each of these are overlapping to form these two bonds, these two molecular orbitals, we will draw dashed lines towards them. And now for the interesting part, the electron filling. So there are two electrons available, one from each atom. So we always start with the lowest energy orbital and we doubly fill it before moving up to the next one. So we have two electrons in that lower energy bonding orbital. And we can get information about the stability of this molecule by calculating the bond order. So we take 1/2 times the number of bonding electrons. So this is our only bonding orbital, the sigma, and it has 2 electrons in it, minus the number of anti-bonding electrons. This is our only anti-bonding orbital, sigma star, and there are 0 electrons in that one. So 1/2 of 2 minus 0 equals 1. So our bond order is 1, telling us that this is going to be a single bond. And this lines up pretty well with the type of Lewis structure we would have drawn for an H2 molecule. All right, let's do H2 plus for the next one. So we'll do atomic orbitals, molecular orbital in the center, atomic orbitals on the side. And these are hydrogens again. We're going to have a hydrogen on the left side, and we're going to have a hydrogen plus on the right side so that we can make H2 plus. It doesn't matter whether the H plus goes on the left or it goes on the right, as long as you specify which one is the H and which one is the H plus. So a neutral hydrogen will have 1 electron in its 1s orbital, and a cation hydrogen doesn't have any electrons. It actually has 0. And so you may be saying to yourself, can I actually overlap an orbital that is empty? And I'm here to tell you that yes, that is a thing that happens, and that is a worthwhile thing to do in some situations. Added stability can be added to an empty orbital by overlapping it with something with an electron in it. So we're going to overlap these 2 orbitals to form 1 bonding orbital and 1 anti-bonding orbital. So it's important to check we had 2 orbitals in and 2 orbitals out. The s orbitals have good overlap, so those are going to be sigma bonds. We'll put a box around this so we remember what molecule we're talking about, and then we need to fill the electrons in. So there's only 1 electron available for both atoms, so our molecular orbital center only has 1 electron in it. And I know that looks weird, and it must feel uncomfortable because so far we've mostly talked about paired electrons, but in order to know whether this molecule actually happens, we need to check the bond order. So we've got bond order of 1/2 times the number of bonding electrons. So this is our bonding orbital. There's only 1 electron in it, minus our anti-bonding electrons. There are no electrons in our 1 anti-bonding orbital. So 1/2 of 1 minus 0 is a bond order of 0.5. So this isn't quite a single bond, but it also isn't quite no bond. It's just half of a bond. So this is a molecule that does exist, an H2 plus. It just doesn't exist very often or for very long because it's not as stable as a singly bonded molecule. So this is the kind of information we're talking about that only molecular orbital theory can give us. Okay, let's do helium, diatomic helium, the cation next. So we're going to have helium and helium, and one of them needs to be a helium cation, so I'm going to put mine on the right. We're going to draw a 1s orbital for each of them. And helium has 2 electrons in its 1s orbital, and helium plus only has 1 because the plus sign indicates it's missing 1. This is going to be dihelium cation in the center. So when we overlap 2 orbitals, atomic orbitals, I guess we can write that in here. When we overlap 2 atomic orbitals, we're going to make 2 molecular orbitals, one of them low energy and one of them high energy. We'll draw the dashed lines so that two orbitals are contributing. So s orbitals have strong overlap. So this is going to be a sigma, and it was made out of 1s orbitals. This is going to be our anti-bonding sigma orbital. And then we'll fill in 1, 2, 3 electrons. So this is the first time we've put an electron into our anti-bonding orbital. So let's take a look at how that affects the stability of this molecule. So our bond order is 1/2 times the number of bonding electrons in this one bonding orbital, which is 2, minus the number of anti-bonding electrons in this higher energy anti-bonding orbital, which is 1. So 1/2 of 2 minus 1, we have a bond order of 1/2 again. So you can see that there's multiple ways to get a bond order of 1/2. Up here, we did it by bonding a half-filled orbital with an empty orbital and only having one electron. Down here, we mixed a full orbital with a half-full orbital, and we had a filled bonding orbital and a half-filled anti-bonding orbital. So having more electrons is not always a good thing, because if you have too many, you start to destabilize that bond. So this one has a bond order of 1/2. So sometimes we see it, but not very frequently and not for very long. So let's do our last example, and that is dihelium, the neutral molecule. So we're going to have helium and helium, and we're going to make dihelium in the center as our molecule. We know that each helium has a 1s orbital where its valence electrons live. Each of those 1s orbitals is going to be holding 2 electrons. And when we mix s orbitals together, we are going to form one bonding and one anti-bonding orbital. One high energy and one low energy. And s orbital overlap is over the internuclear axis, so we're going to get a sigma bond formed out of 1s orbitals and a sigma star formed out of 1s orbitals. And now we have 4 electrons to fill in. So we have 2 electrons down here and 2 electrons up top. So our whole tiny molecular orbital diagram is filled. So let's look at how that affects the bond order. We have 1/2 times the number of bonding electrons in this orbital, which is 2, minus the number of electrons in our anti-bonding orbital, which is 2. So our bond order ends up being 0. And a bond order of 0 means that there is no bond. And this might make sense to you because we spent all of the Lewis structure chapter discussing the fact that helium doesn't bond with other heliums because it already has the number of valence electrons that it needs. So this gives more specific proof as to why that doesn't happen, because its bonding orbital and its anti-bonding orbital are equally occupied. And that means that all of the potential bonding cancels out. We have a bond order of 0. So these are the only molecular orbital diagrams you are going to be responsible for understanding in this course. This is just an introduction to the basics of molecular orbital diagrams. Orbital diagrams with more orbitals and more electrons in them will be a topic for a future chemistry course.